Good morning, AP Physics students. We're going to be doing a little bit of a different lesson today because I want to start doing labs and we don't really have access to our lab equipment. So we're going to be doing some virtual labs. So I thought that would make things a little bit more interesting than just a lesson with a lecture and then the homework assignment, kind of what we've been doing the last week. Office hours went really well. They're optional. They are every Tuesday and Thursday and Friday from 10 to noon. It's basically just a chat room. I have a whiteboard. I can draw physics if you ask me a question, confused with how to do any of the skill checks that are required online. Everything I'll still accept. So if you got some zeros in the grade book, you can start doing those assignments and I'll check them about once a week and drop them in. But yeah, everything is working well so far. We just need everyone to keep up because it's not spring break yet and we still have a lot of stuff to do. All right, so heading into this lesson, we're looking at a graph. And because this is an AP Physics 1 multiple choice question, and you can tell because it's got a giant paragraph and a huge graph like they all do. I'm not going to give you any hints other than that it talks about the center of mass of a system of particles. Just basically ignore that and just think of this as one object, and it's fine. It really is behaving that way, and you'll get the right answer. And that's how they want you to do the problem anyway. But other than that, you're on your own. And then for this one over here, this is not a multiple choice question, and it's two objects. They're connected by a spring. The spring's gonna release, and one's gonna go flying that way, and one's gonna go flying that way. And I said that if this one has a velocity of v, what is this one's velocity after it goes flying? So see if you can use conservation of momentum to get that answer. You don't need to use any spring equations. All right, I'll give you some time to do that. You hit pause and then hit play when you're ready to go over the answers. Okay, so for the first question, it's important to remember that when we're given a graph, we have to figure out what type of graph it is. And in this case, it's a position versus time graph, actually. So that tells us where the object is. It starts with a position of 8, and then it has a position of 12, and then eventually it reaches a position of 9. Doesn't really help us, but that's the information we can read. We can also read that the time it takes for that to happen is 5 seconds. What are they asking us for? Well, they want to know the change in momentum. Well, the change in momentum is velocity final minus velocity initial. So that means that we need velocities, not positions. Well, we can actually take the slope of a position graph, and that gives us velocity. So that's our strategy. So we take the slopes of those two lines. We get +2 and -1 to be the slopes. And then we can plug those into our formula because our final velocity is -1. Our initial velocity is 2. Go ahead and plug those in down here. And we can plug in the mass they gave us. We can see that the change that occurred is -18 kilogram meters per second. All right, next question. One of those variable style questions. So it looks hard because there's no numbers, but it's really not hard. We just solved it for all numbers, and you get the same answer no matter what you use for m. And so if you really struggle, you could just call m 1. But what you'll see often with these questions where they leave m is that you can divide everything by m and it disappears, which is exactly what happens here. So we start off, we write momentum initial equals momentum final. Our initial momentum is 0 because we are not moving. So our final momentum is actually equal to 0 even though we are moving. That sounds a little odd, but you got to remember that it's the final momentum of the system, and momentum has positive and negative aspects. So our starting momentum is 0 and our ending momentum actually adds up to 0. Let's see what happens. So our first object, they gave us the mass of 2m, and they say that it leaves with a velocity of v. So that's what I put right here, mass times velocity. And then for our second object, we know it has a mass of m, but we don't know what speed it's traveling at. And so at this point, we can start solving. Cancel out the m's, like I mentioned earlier, move 2v to the other side, and we have our answer is -2v. So basically, the final momentum of both objects is equal. Because whatever the change that happened to one object, that has to be the exact same change for the other object, since their momentums need to add back up to 0. All right, so let's take a look at the simulator that we're going to be using. And there's more directions on the actual, oh, not more directions, but the same directions are on the actual handout that I provided for the homework, but I also have it in the notes. Oh, before we get to that, some vocabulary. So elastic collisions. So the two things we're going to be talking about are inelastic and elastic collisions. And when you hear the word elastic, I want you to think about like elastic clothing. Elastic clothing is like stretchy clothing, like sweatpants and pajamas. And so in an elastic collision or a stretchy collision, uh, objects bounce off of each other and kinetic energy isn't destroyed. It's conserved. And so this happens whenever you have bouncy balls, or basically just bouncy balls when they bounce off of each other. Now, the thing about elastic collisions is in the real world, they don't really exist because energy gets lost to things like sound. So for a collision to be perfectly elastic, it would have to be dead quiet, cause no heat, a lot of things that a collision can't really do. But when two bouncy balls bounce, so little energy is actually lost that you can basically say that no energy is lost. So it's okay. So in our class, we treat it as if actually zero energy was lost. And when you hear the word elastic, almost all the time, they mean perfectly elastic, meaning that no kinetic energy is lost. It's a bouncy ball collision. All right, so what's the other type of collision? Well, inelastic. Inelastic means the opposite, means energy is lost. And the way energy is lost is typically it's lost to things like sound and heat, but also work equals, tried to grab a different color there, work equals force multiplied by distance. And when cars crash into each other, as they drive into each other, they exert a force over a distance as they crunch. To bend a car takes work. And so that's why bouncy balls are elastic collisions, is because when bouncy balls bounce off each other, they don't actually destroy each other. And so they don't do any work. But in an inelastic collision, they destroy each other partially, and work happens, which means we have to lose kinetic energy. So if the objects get destroyed during the collision, it's inelastic. If the objects stay the same, it's closer to elastic. So like if you're playing pool, like on a pool table, the little pool balls, when they bounce around, fairly elastic because they don't change shape. But if they were made out of clay or Play-Doh, they would be pretty darn inelastic when they bounced off each other. They would stick to each other, which actually brings us to our perfectly inelastic collision. When a collision is perfectly inelastic, that means that it actually, the objects stick together, and that will cause the most energy to be lost. So if you have two objects and they actually stick together, that's perfectly inelastic. Okay, so for our little simulator, we're going to be doing the green one, perfectly inelastic. So we're going to need to set the we're going to have to set the elasticity to 0. And so let me show you what that looks like. All right, so here's the simulator itself. I've included a TinyURL link, as well as the link to the actual simulator. One of those should work. I'm also going to put the link straight up on E2SD, so that should work fine. Just click that. All right, so this is what the simulator kind of looks like. You have a couple of cars, and you can specify their masses. So you do have to change the mass of the red car. You can do that by clicking those buttons down there. The other thing you need to do is set the velocities. You can obviously change those right there. The graph isn't great. It doesn't say exactly where the lines are, but these give you very accurate numbers. So you're going to be reading the velocities off there. The things that you need to be measuring are momentum, which is mass multiplied by velocity. And for the simulator, I checked things out. M clearly equals 1 kilogram, how it's programmed. And so that's what the mass of the cars is 1. So for instance, this one right here, if those are the actual numbers, the chart talks about the system's momentum. Right now, the momentum of the system, well, we can look on the graph and we can see that the momentum of the system is clearly 1 because the car has a momentum of 0. It has a mass of 1 and a velocity of 0. That's for red. The momentum of blue is a mass of 1 and a velocity of 1. So it has a momentum of 1. So the total momentum of the system is 1. So that's what the chart that I have on the homework. It doesn't ask you to do like the momentum of either of the individual. It just cares about the momentum of the system before and after. And you can see in this example that the momentum of the system before was 1, and then after it was still 1. So momentum was conserved. Um, Now, unfortunately, this is really kind of a terrible example. I'm not going to go back and record this, but the problem is right down here. For our lab, the elasticity needs to actually be set to 0, where it was set to 1 for this little example. So make sure you actually set it to 0. I'm going to have warnings all over the place, but if you set it to 1, it's not going to work at all. So make sure you set it to 0. In some ways, I like that it's not set to 0. You have to go online and see what happens when you set it to 0 yourself. But make sure you actually set that. The other thing you're going to be doing is calculating the kinetic energy before and after. Kinetic energy is 1/2 mv squared. You can tell it to graph energy, but it doesn't give you it doesn't really tell you what the values are. It just kind of throws it on this graph, which doesn't show very much. So you should just calculate the energies by using mass as 1 and reading the velocities right here. Let's see here. I think I have another slide. I'm going to erase kind of all of this except for the elasticity thing. It's really important that you set it to 0. Okay. Yeah, so here's the actual lab itself. And like I said, it's really important you set the elasticity to 0. You're going to be reading the velocities. So these are the initial velocities. And so you'll use that to calculate the before, and then you have to read the final velocities, and you'll use those to calculate the information after, and then answer the questions. I included the answer key as always, but this time I only included kind of like the answers to 2 and 3. I want you to fill this out so I can kind of see if kids are really doing these or just copying the answer key. I didn't fill out the chart at all, nor did I answer number 4. I want you to take a stab at them. I think it's really important that I try to make it difficult to just copy down the key, because it's really easy to just do that, and that's going to really hurt you when we come back together, which I strongly think we're going to, and have some tests. So hopefully I'll see you guys in May. Keep up the good work. Those of you that are handing things in, those of you that haven't handed much in, I'll still take everything, but you need to start working on it right away. Okay, I'll see you guys tomorrow, or I'll see you in office hours.